start streaming. Okay, just I'll check once if it is streaming properly. Just I'll check once if it is streaming properly. Okay, so today's session would be, last day we introduced Riemann integrals and fundamentals of integrals. We showed that integration was the inverse of differentiation. We showed fundamental theorem of calculus, and we also showed that integrals meant dividing small areas, dividing area under a curve into small areas and summing them up, right? So integrals were meant to actually find areas under curve or any arbitrary surface, and we solved a few problems regarding that. And we also showed that the area under the curve was equivalent to the conventional integration, the conventional integration that we performed. We also showed we understood the fundamentals using Riemann integral and how we can solve limits of a sum. These are the things that we actually covered last day, and we saw several limits of sums. How can they be approximated by integrals by making them area operations? So today what we'll do is, and I also introduced, I hope you remember, the Newton-Lebnitz theorem using the fundamental theorem of calculus. And I said that more than the fundamental theorem of calculus, you'd find it useful to use the Newton-Lebnitz theorem, right? Because it's often people try to find derivatives of functions with integrals. So we'll start off with the fundamental theorem of calculus's corollary, that is the Newton's Leibniz theorem. Do you everyone remember the Newton-Leibniz theorem? I hope we proved it last day, right? So we proved that. So phi 2 and phi 1, if the limits of the integration are functions of x, and we are integrating some function, so we get is phi 2x derivative of the second of the upper function, or which is the upper limit, minus phi 1 of x derivative of the lower function in the lower limit. This is what we had proved using fundamental theorem of calculus. Very simple proof, very basic. So we have shown it last day. If you haven't checked out, you just can go and see that if you're interested. Let's start. So first question it asks you to find out the derivative of. So we'll start. Today will be mainly problem solving, and then at the end of the class, so Mr. Pandey, you had written a mail to me, so I have responded. Have you seen that? So have you used that software?
Yes, sir. It is happening.
Yeah.
So I can solve your problems. Yeah. Thank you, sir.
So we'll also do those
sir,
problems.
You said you will. Yeah. You said you replied in email that you will solve.
Yeah, we'll solve those few problems from that list, sir. Also. Apart from, I will pick some of them up, but we will be solving them mainly theoretically by drawing hand figures, and sometimes I may come up with that computer program to just visualize a couple of them.
Okay, sir.
Because what you need to understand is you can't draw figures for everything. Once you understand first derivative, first variable calculus, you will be going to higher variables where you will not be able to draw figures for everything. So you will have to generalize once you understand the basics. So we'll draw some basic figures using the tool, and then we'll be trying to solve them like by drawing abstract figures, sort of a thing. Because we have reached that part of the class where you should have an abstract idea of what integrals and derivatives and calculus is all about. So I have reinforced this idea that calculus is breaking down difficult problems into smaller problems and solving those smaller problems. So anyways, that's a long story short. So we'll solve the first question. So So it's a easy question. So I'll, if anyone wants to volunteer, they can, or I'll just start right away. So we are solving this. You are told to find the derivative of the function, which is given by this implicit form at pi comma pi. So what would I do first? Any ideas?
Leibniz theorem.
Leibniz rule.
Okay, so you are suggesting take the derivative on both sides, right? So let's
Yes, sir.
take derivatives on both sides. Both sides, what you end up with is just put the value of the top function into the in the inner function. You will have 1 3 minus 2 sine square x, right? You just put x, the top function, in the place of t, which is the inner function with which you are solving the integral, and then you take derivative of, I'll just underline for the first, because this is the first we are applying this theorem, ddx plus, you will be putting cos of y. So now what will we do? So I'll just draw. Now what do you think we should do? So we would also take the derivative of dy dx, right? dy with respect to x, and we'll set this to 0. So the red that I have written here, the red signifies the derivative of these two functions, right? The red that I have written are these two products, and the green and the blue that I have used are these two, the first part, right? And okay, is my screen not visible? Okay, now it's visible, right? Okay, so what happens is, so you see ddx will be 1. So you see the lower part, the lower limit has gone to 0 because they were constants, right? The derivative of constants are 0. Right, so the second part, the lower, the phi 2 ddx of pi by 2 is 0 and ddx of 0 is 0. So we will not be, this is the first time we are doing it, so I'm doing it step by step, and after that we can skip some steps. So this turns out to be dy dx is equal to minus cos y by, or rather 3 minus root over 3 minus 2 sine square y by cos y, right? And the negative sign. Agreed? Any doubts? So I'm just solving this equation, making dy dx the subject, right? So now you're told to find it at pi comma pi. So what would be the answer? The value of the function on the right at pi comma pi? So it's
Root 3.
minus root 3, correct. So cos y, oh sorry, yeah, so my correct, cos pi is minus 1 and you have a negative on the top, so, and sine pi is 0, we all know that. So you dy dx turns out to be root 3. Do you understand? Do you any one of you have any doubt? Please, if you have a doubt, you can ask. Then otherwise we'll go to the next question, which is, and next question I'll ask some of you to help me out, because I've already done one of these. Is it okay? Is it clear to everyone?
Yes, sir.
Yeah, except the two of you. Anyone else? Do you have any doubt other than Hedvi and Mr. Pandey? Because I don't want you to fall behind in the class, because we'll be doing few more questions related to this. Okay, no one is asking any question. Good. So I'll just copy these two questions and I'll solve them now. Let's solve them one at a time. So let's solve the first limit question, question 2. So you see, you have the limit of the form 0 to x t log of 1 plus t by t to the power 4 by 4 by x cube. Can anyone tell me what is the limit of the form of, so, and why?
Sir, it's 0 by 0 form.
Why? The
Sir,
denominator
because,
is 0, I agree, but numerator is, why?
And matlab, both the limits are 0.
Correct. So
Upper
you are
limit and
integrating
lower
to the same point. So you are from 0 to say a. So you will have, if this function is if this integrates to some function capital F of x, so you will have f of a minus f of 0 for a continuous function, limit a tends to 0 plus, or whatever you are taking it to be, this is going to be 0, right? By the definition of continuity, agreed? What two
Yes, sir.
which two definitions did I apply here? Anyone? So one definition I applied is fundamental theorem of calculus. So if this is f of x, right? If this is f of x, theorem of calculus. By this I mean this without the limits. F of x is this without the limits. I applied the fundamental theorem of calculus. Number 2, or you can write f dash x as this. So this is the better way of representing. F dash x is the function in the derivative, right? So, and number 2, I am using limits. Limits, continuity of limits. Continuity. Both of these I am using, and then I am saying it's a 0 by 0 form. So 0 by 0 form, will use the L'Hopital's rule. And what is the rule saying? Limit x tends to 0. You take the derivative of the top function. What do you have? T log of 1 over 1 plus x by x to the power 4 plus 4 divided by x cube. Agreed? Any doubt? Ravi, do you have a doubt?
Sir, 3x square.
Yeah,
in denominator.
yeah. The numerator is okay, right?
Yes, sir.
Yeah, great. So to numerator, we are denominator. I had forgotten to take the derivative, so I use the derivative of the numerator and the denominator derivatives. So now x square and x cancels out, so you are left with limit x tends to 0 log of 1 plus x to the power 4 plus 4 x into 3. So now what do you use? It's still a 0 by 0 form, right? But you have a well-known limit here. Can you identify it?
Sir, ln 1 plus x by x is 1.
Correct. This is 1. We have used this multiple times. So log of 1 over x plus 1 plus x by x is 1. So ln x will go away, ln 1 plus x will go away, and you'll be left with, now you have no problem with putting x is equal to 0. So this is, if you put 0, you get 1 over 12. Right? So we'll solve 2 questions in no time. Good. The third one, let's ask someone new to do it. So you are told to find the derivative of this. So f dash x is equal to, yeah, Ravi, go ahead. If you want, you can come up and answer. What would be the answer of this? This is one of your assignment questions. Okay, people are not replying, so I'll start. So first is, I'll just put x square in the place of t. and I will take the derivative of x square minus cos inverse x plus cos of cos inverse x ddx of cos inverse x. So what would be the first derivative? First one is square root of x square plus log of cos of x square into 2x, right, minus cos inverse x plus x. So cos of cos inverse is identity, right? That's how you have defined cos of cos inverse x is equal to x. You are doing an inverse operation into ddx of cos inverse x. So what is ddx of cos inverse x? So let's try, let's do it, or does anyone remember? Root over of
minus of under root 1 minus x square.
Correct. So let's let's try this once. Cos inverse x derivative. I think I had done it before. So in case you forget any time, so I'm just showing how to come up with the equation of these derivatives. So you take cos on both sides, you'll be left with cos y. Now you can take derivatives, right? Dx dy will be, or rather dy dx also, or let's write dx dy. Dx dy is minus sin y, right? Or dy dx is equal to minus sin y, which means that sin y is equal to root over of 1 minus x square, right? Because sin square x plus cos square x is equal to 1. Agreed? 1 over x square. So I'll just put it here. So you have 2x x square plus cos x whole square, cos x square, not whole square, sorry, plus cos inverse x plus x by 1 minus x square. You have a minus, so this becomes plus. Is it okay? Understood? I'm just finding this derivative over here and just putting the value over there, right? Okay, shall we proceed? I'll wait for a few seconds. If anyone has a doubt, ask, or we'll be proceeding to the next part of today's class, that is solving some indefinite integrals. So we have done a lot of definite ones and also Newton-Lebnitz. So let's do some indefinite ones also, that they are also relevant. So let's try to find out a family of functions when you do an inverse, also known as an antiderivative. So I see there is no doubt regarding this. I think you found it very easy. So okay, so 3 of these are done. So we'll do some antiderivatives. For example, I'll just briefly tell you integration by parts, and because I think you all know what is integration by parts, the formula at least, and we'll be solving some question related to that. But and then we'll be doing something called as a partial fraction. So we'll be some indefinite integrals we did last time, and I have a few of them written today. You can try them to try to prove them by the substitution rules that we had written last time. We had proved by substitution, but today we'll be doing some more advanced indefinite integrals. Substitution we have already done last day. So the proof of this UV rule. So what you need a bit of back calculation to find the UV rule. Why do I say that? Because the UV rule for the derivative is taking derivative of one function and keeping the other constant, right? So when you take the integral of a product of functions, you will have to build a function such that the derivative would hold. For example, I tell you that if you have a function, say u and v, and you're integrating those with respect to dx, so what does it have is, what do you have in turn is, you integrate one function and differentiate the other. This is the way you should remember it, and proof I'll give you now. So you, for example, I am integrating this. So whenever, if you don't remember, just write it this way and differentiate this. So whichever is integrated, you have to integrate that function twice. For example, you have integrated this function, you will be, the first function you will be keeping the same, which is which you are supposed to differentiate. So Vx integral of ux dx minus, so this the other function that you are supposed to take the derivative of v here, and with the product of the integral of the function, right? What does this mean? We'll be solving a couple of questions. It will become very simple and easy to understand. So one function will be taking, that will be always integrated, one function you will always differentiate, and then this product will again be integrated, right? So let's see what does it mean, why is this correct. So let's consider the function capital F of x as Vx integral ux dx minus dv dx integral of Vx dx whole integral of dx, right? So first you need to take this integral and then you have to take the other integral. So I'll take the derivative of this function. So what will be the derivative? Can anyone help me with it? So the first function, we can use the UV rule, right? Hello, am I audible? Okay, yeah.
Yes, sir. UV rule.
Yeah, you are. I'm just asking. I'm audible because everybody is silent for a long time. Okay, so ux, it's very difficult otherwise to know people are there on. I mean, I am there in the call or not, or I'm speaking directly to the TV with the screen. So it's good that you interact. Otherwise, it becomes difficult to understand whether I'm in the call. Okay, so UV rule. So I'll say first differentiate this function. You get u of x, right? And plus of dv dx u of x dx, right? Now
Yes, sir.
take the derivative of the second function. So people, what they did is they did this back calculation. If you take the derivative of the second function, what are you left with? Dv dx integral of vx, right? So these two are same.
Yes, sir.
So you are left with uv. So this is what we are doing. So this is the f dash function. So we are seeing that our choice of the antiderivative is correct. So this is what I wanted to prove. So good. So let's solve some questions related to this. So some warm-up questions. For example, the first one. This. So you are told that, see, this in general is a non-integrable form. Right? This is a non-integrable form. You can solve it analytically, but it's not typically integrable. So you cannot do it, you cannot do a antiderivative of this. Antiderivative is a very complex function, so it is not a real function. So that's what is called as a non-derivative, non-integrable function. So you see is this function I am approximating this as k of x, right? So this is k of x, or the k function. This k function has been told to you. So you are told that you know the value of this function by some oracle, and you're told to find this integral. So any ideas? So since it is under the integration by parts, so by the theory of lectures, so this will always be, you have to use integration by parts. So you tell me, just joking. So so which will you take? So hello. So there was a technical glitch and the video had stopped recording. So the original session was 2 hours and we discussed all the problems. So the rest of this video I'll be trying to redo the problems that we had done during the session, the remaining 8 problems that were left. So let's start. So we were talking about the integration by parts thing. So we showed that this is that formula of integration by parts, right? Taking the derivative of the right hand side. So we took the derivative of the right hand side and we found that this is equal to u Vx times ux plus dv dx integral ux. So this is what the second part of the derivative turns out to be. These two are same, therefore you get uv. So since you have uv of this part, we were discussing that since it is so the integral of uv could be written as this, the right hand side, which is a correct assumption for our problem. For the next question, we'll be taking k is equal to e to the power t. This function is given to us and it is not integrable in general. So, but we are told to find this function's integration. So k is not integrable in general. So we are assuming that k is given to us by some oracle. So what happens is, so it's given to us by some oracle, and then we assume that it's useful. So for example, let's see. So how does it become useful? So we'll use integration by parts. So remember that one part is a, say, u and v. The easy way to remember is one you integrate, the other you differentiate. So for example, this function, the integral of e to the power t log of 1 plus t dt. So this is easy to integrate, as the integral of e to the power t is e to the power t, and this is easy to differentiate. This is equal to e to the power t log of, so I'm just writing this for this case, log of 1 plus t. You keep the first part same, and the integral of e to the power t dt, and ddx of log of 1 plus t is, let's write it down, ddx of log of 1 plus t. So this is nothing but 1 plus t. So this turns out to be e to the power t log of 1 plus t minus integral of e to the power t plus 1 plus t dt. This is given to us as k. So this is e to the power t log of 1 plus t minus k plus c. So this is a simple problem that shows us how to use integrals, integration by parts. Now number 5, the integral of sin x log cot of x by 2. So the question arises, which one do you take as the integration, which one do you integrate, and which one do you differentiate? So it turns out, so sin x is easy to integrate, we all know that, and cot x is log, this would be simpler. So we will integrate this one, and differentiating this one is okay. Differentiating is okay. So we'll differentiate the second part. So let's see, log of cot x by 2, if you differentiate, you get 1 by cot x by 2. Derivative of cot x is cosec square x by 2 into half. So the negative of cosec square x is the derivative of cos x. Similarly, so the cos x you can write it as 1 over sine square x by 2 into cos x by 2 into sine of x by 2 to half. So this cancels out and you are left with 1 by sine of 2x into x by 2. As we know, sine x into cos x into 2 is sine 2x. So this is 1 by sine x negative. So the integral becomes, sine x's integral is minus cos x. Now we'll not write down the entire thing. So what we'll do is we'll only write the integral directly. So log of cot of x by 2 minus, so the integral is again cos x and the derivative is minus sine x, inverse of minus of sine x, 1 by sine x as it. So 1 of cos x log of cot x by 2 plus integral of cot x dx. So this turns out to be minus cos x log of cot of x by 2 plus log of sin x plus c. So log of sin x is cot x, so you can just do a simple check to check that. So derivative of log of sin x is be 1 over sin x into cos x, assuming x is greater than 0, and that is equal to cot x. Simple proof. So this is we'll be doing many more integration by parts problems today, but for the time being, let's assume that let's take this for the integration by parts, that warm up for integration by parts. So this next part that we'll be solving is partial fractions. So partial fractions are when you have a fraction written in form of p by q that you have written over here, you can break it up into multiple fractions of the form that if q is a product of multiple factors. So for example, it's a linear polynomial with k degree, so you can have k factors. With it's a r degree quadratic, so you can have r factors, and so on. So the idea is, so you break up all the possible combinations in the denominator so that the LCM turns out to be your original equation. So for example, we'll do question number 7. It will become a bit clear once we start that. So for example, dx x plus 2 x square plus 1. So once we solve this question, what it means would become clear to us. So what does this mean in general? It means that you can write any polynomial or ratio of polynomials as, so this is your this is the numerator, so your numerator will always have a lower degree than your denominator, plus bx plus c, because if it is more, you can always divide off the numerator to get a lower degree. That's the idea. So bx plus c you get here. So now what you do is, you can easily solve for this equation by doing a cross multiplication. So you get a x square plus 1 plus bx plus c x plus 2. So you see you have two equations that you have for you. Now you have an equation in form of x. Then you have three unknowns a, b and c. So to get the three unknowns, you need minimum of 3 equations. Therefore, to get 3 equations, we can put any value of x in this equation and get a solution for it. See, the easiest one is to use a root. X is equal to minus 2. If I use that, so you will have vanish. You will vanish this part. So you will be remaining with minus 2 squared plus 1 is equal to 1. So you will have a is equal to 1 over 5. Similarly, putting x is equal to 0, that again vanishes a lot of things. So you get a of 0 plus 1 plus c into 2 is equal to 1 again. So this turns out to be 2c is equal to 1 minus a, or c is equal to 4 by 1 minus 1 by 5. So I'm just putting the value of a here, and you get 4 by 5 by into, that is 2c. C is equal to 4 by 5 into 2 is equal to 2 by 5. This is your c value. And how do you get the value of b? So you need to put another equation. So we have current equation turns out to be 1 over 5 x square plus 1 plus you have is b a value you do not know, plus c is 2 by 5 into x plus 2. So what you can do is take a easy value. For example, x is equal to minus 1. This will become 1. So it's easy to calculate. So you get is 1 is equal to 2 by 5 plus minus b plus 2 by 5. So you get minus b is equal to 1 minus 4 by 5, or b is equal to minus 1 by 5. So once you put everything together, what you get is 1 over x square plus 1 x plus 2 can be written as, so a's value is 1 over 5 1 by x plus 2. I'm just putting it in this equation. And why am I doing it? It becomes easy to integrate, as we have seen before. So 1 over 5, that is the value of b, into x, you have a negative sign, x square plus, what is there, plus 1 dx plus 2 by 5. So you have putting the value of c now, integral of dx by x square plus 1. So these two will give you integral 1 over 5 log of x plus 2 minus. So what we will do here is we'll be substituting this as d of x square plus 1, which is equal to 2x, and we only have x here, so we'll divide by 2, right? So if we divide by 2, it's so we know d of half x square plus 1 would be x. This is the idea. So 1 over 10 log of x square plus 1, this will turn out to be plus 2 by 5. 1 plus x square is tan inverse x. So this is how you use a partial fraction. So each of the smaller fraction becomes simpler to calculate. This is the idea behind using a partial fraction. So what you end up doing is you calculate smaller problems. So instead of a product of polynomials in the denominator, you take all the possible polynomials in the denominator and break it up so that each individual integral becomes easy to compute. For example, let's do number 7 now. So in case of number 7, what do you have? So number 8 as I mean. So you have this equation. Let's see. So the equation is this. So in this case, using a partial fraction may be very, very detrimental. So you see 12x by x minus 1 cube into 2x plus 1 plus 1 minus 1 is equal to a by x minus 1 plus b by x minus 1 squared plus c by x minus 1 cube plus dx plus e x square plus x minus 1. So you see you have 5 equations here. So if you do the cross multiplication, you need at least 5 equations to solve this, which would require a computer to do in general cases, like it's maybe very, very difficult to solve. And regarding the previous question, so x square plus 1, we could have written it as x plus I, x minus I, but we are avoiding integrals which have a complex part of it. So if they have complex part, they can be converted into simple part during Euler equation, but we will not do that. So that's why we are breaking up into fractions where the numerator has a degree less than the denominator. This is because if it has equal or more, you can always have a square of that degree and cut and reduce that into a degree lesser than that by normal division. So this is because you can directly take LCM of these two, and once you take LCM of these two, you have a degree 2 polynomial, and you also have a degree 2 polynomial, and so you can remove the degree 2 and get back whatever you want. So now in this case, what would be the trick? So you have the numerator as x and denominator as x cube. So we will use something like this. So this let us write as p, this as r, and this is q. So if we have a fraction written as p by q plus q into r, so we will use, say, p by q can be written as q quotient plus remainder by q. So if p by q is equal to quotient plus, so we are using the normal division method. So if we divide, any dividend can be written as a product of the quotient into the divisor and the plus the remainder. That's what we are writing. So what we have is, so instead of doing a partial fraction, which is directly by solving for the a or b or comparing the you have something like you're comparing You could compare coefficients of bx on the left and the right hand side and get their values. Instead of doing that, what you can do is you can directly do the division in these cases. So in this case, when it's very difficult to compute, so what will you do? So in this case, we want our function to be simple, but x minus 1 cube is not simple, as in you can't directly divide the numerator, can't directly divide the numerator. So we will substitute x minus 1 as t, so dx is dt, or x square plus x plus 1 or minus 1 is t plus 1 squared plus t plus 1 minus 1, which is t square plus 3t plus 1, right? So 1 plus 1 plus 1. So this is what we get. So if we can substitute, 12x will become 12 into t plus 1. So your new integral turns out to be 12 into t plus 1 by dt by t cube t square plus 3t plus 1. Now you see, this becomes a simple problem. If we are able to get a numerator of any form, this t cube will do the job by dividing it. So the idea is, I want to divide 12t plus 12 by t cube plus 3t plus 1 and write it as p plus some quotient plus r by q, and I want rt to have degree of rt to be more than 3. Why? Because I have a t cube attached to the denominator. Since I have a t cube attached to the denominator, so if I have an r cube degree greater than or equal to 3, so I will cancel off more or less all terms of rt greater than or equal to 3. Let's see what we can do. So it's something like this we'll do. So we'll divide a normal division, 12t plus 12 with t square plus 3t plus 1. So we'll start off by removing t to the power 0. Remove t to the power 0, then t to the power 1, then t to the power 2, and then t to the power 3, and so on. You will start on removing until and unless you get t to the power 3 and higher terms. So let's see how we'll do it. So if you multiply 12, so t to the power 2 will be removed. So you'll be left with 36t plus 12 plus 12t square. So you have is minus 12 24t. These two cancels, minus 12t square. Now my idea is to remove the t term. So how do I remove the t term? I'll again subtract 24t. If I write 24t over here, so this 1 becomes 24t, your 3t becomes 72, as I can see, it's 3 into 24, 3 into 24, and your t square becomes a negative of 24t cube. So you see, this 2 will cancel, this becomes 60t square plus 24t cube. Now you want to remove the t square term. How do you remove it? Again, you multiply 60t square. So the first term will become 60t square plus 180t cube plus, so 3 into 60 is 180 plus 60 t to the power 4. So this turns out to be, if you subtract, minus 156 t to the power 3 minus 60 t to the power 4. So this is what we will calculate, and once we have this, so we can write this, put it into this equation, right? So you will now see the complete picture. So why is this important? So once I put it in this equation, I get 1 by t cube t square plus 3t plus 1, numerator is 12t plus 12. This can be written as 1 over t cube. We have put the integral also. So t cube in bracket What is the quotient? The quotient is this. This is your q. So you will have 12 minus 24t plus 60t square. Next, you will have is, where is it? Yeah. So this is your remainder. So minus 156 60t to the power 4 by your divisor. So this is your equation that you will be getting. Now see, this question has become such a simple question. So you will be ending up with 12 by t cube dt minus 24 by t cube t square dt plus 60 by t dt minus integral of 156 minus 60t by, or plus, this is plus because both are minus, t square plus 3t plus 1 dt. So you see, this is a simple integral. So t to the power minus 2 by minus 2 into 12 minus 24 by t to the power minus 1 by minus 1 plus 60 to the power log t minus integral of 156 plus 60t by t square plus 3t plus 1 dt. So this becomes minus 60 square minus 24 or plus 24t plus 60 log t minus I of t, I2 of t. So I2 of t is your integral of t square plus 3t plus 1, and the numerator is 156 plus 60 t dt. So we'll again use the old trick that we have, that is, we try to make this dt the denominator. So you see, d of t square is 2t. So the numerator has a degree of 1. So we can use some factors to do here and there manipulation and get the numerator to be what we want. For example, so you see d of t square plus 3t plus 1. What is it? This is, I want this as the dt, right? This is the idea. This is 2t plus 3. So if I multiply this with 30 on both sides, I will have is 60t plus, of course dt is there, 60t plus 90 dt, right? So this is not enough yet. So you will have 30 into d of t square plus 3t plus 1 plus, if I add 66 dt on both sides, I get 60t plus 90 dt plus 66 dt, which is equal to 60t plus 156 dt. So this is the idea. So which is what we want in the numerator. So we need to replace the numerator by this term. So we replace this. So we get 30 times d of t square plus 3t plus 1 by t square plus 3t plus 1 plus 66 dt by t square plus 3t plus 1. So now this is a simple problem. This is log of t square plus 3t plus 1 times 30 plus 66 times. So we'll need to make the denominator a perfect square. You remember we had something like x square minus a square. So we remember this formula, right? Dx by x square minus a square is equal to 1 by 2a log of x minus a by x plus a. Or we would like to have a formula like this, where it is 1 by a tan inverse x by a. So both of these, one of these we would like to have. So we'll make it a perfect square. So dx by t plus 3 by 2 squared. So you have, this is t square plus 3t plus 9 by 4. You need to make it 1. So you need to subtract root 5 by 2 squared. So it's this formula that you'll be using. So you'll be turning out to be 30 log of t square plus 3t plus 1 plus 66 by 2 into root 5 by 2 log of t plus root 3 by 2 minus root 5 by 2, right? T plus root 3 by 2 plus root 5 by 2. So once you have done this, you put everything together. So the first terms, we will write this as I1t plus I2t and replace t is equal to x minus 1, and you'll get the original or the final answer. This is the way you need to solve. So what we did is, to account for the large number of variables that we need to solve normally, we divided the term to get the, we divided this 12x by this term after substituting x minus 1 as t, and we got powers. This became the quotient, and the remainder we wanted powers greater than equal to 3 degree, and we got it. And we also wanted it less than 5 because we wanted only 3 and 4, because we will divide by 3 cube, it will remain cube, and 4 cube power will remain and the fourth power will remain. So this is why we stopped at 3 and 4, because we will be dividing by t cube and having only t term. Otherwise you could have just continued removing t cube and gone higher, right? You could have multiplied 156 t cube and gone higher, but we are not going to do that. We kept to 3 and 5. 3 and 5 because x to the power 3 plus ax to the power 3 plus bx to the power 4 by t cube by x to the power cube is a plus bx, where the denominator, originally the denominator is a cx square plus dx plus e. So if we have the numerator as a 1 degree lesser than the numerator, denominator as a 1 degree more than the numerator, so we can use the trick that we used here, that we took the derivative of the denominator as the numerator and wrote it as a derivative of the log. This is the idea that you will be using for a normal differentiation in a partial fraction sense. Okay, so next what we'll do is, we'll be going to some problems related to some definite integrals. We have been doing indefinite integrals, and we have also solved questions related to UV rules and on the Newton-Lebnitz theorem. So now we'll do some definite integrals, right? So we'll be solving this set of definite integrals now. So we'll have 2 questions from the definite integral and 2 from area, and then we'll call it a day. So the 2 questions from definite integrals are this. So the first question and the first question is this, number 9. So as soon as you see this question, right, so this you should understand what to do. So you may think you may do integration by parts, but I have told you log x plus 1 by x is not integrable. And I have told you something like this as well, 1 plus 1 by x is equal to minus 1 by x square. So you have a denominator of 1 by x square. Can you manipulate the interior of the log to get a 1 plus 1 by x? It turns out yes. Immediately 1 by 2 to half log of, you take x common, and you will, if you take x common, so you will have this becomes 1 and this becomes 1 over x dx by x square. So what does this equation become? So half 1 log x by x squared dx plus integral of log of 1 over 1 by x dx 1 by x square from half to 1. So let's solve the second integral, which is much simpler. So this is the trick that we used only to get this integral, right? So now this integral can be written as half to 1 log of 1 plus x d of 1 plus 1 by x, and you put a negative sign because d of 1 plus 1 by x is equal to minus dx by x square. So but you have a plus, so I am just putting a minus to account for that. So now you just put this value as t and this as t. So if you do that, so what does your limits become? So limits become, so this limit x is equal to half, t is and x is equal to 1, t is equal to 1 plus 1 by x, that is 3, and this is your 2, because this is 1 plus 2, this is 1 plus 1 by 1, this is 1 by 1 by 2. Okay, so this integral can be written as, so this I2 can be written as integral of half to 1 log t dt, sorry, pardon me for that. So I will write it from 3 to 2, right? Or if you take the minus sign with it, so minus this, or I can minus of this, and I can just replace the limits, right? So because if you by the fundamental theorem of calculus, it's f of 2 minus f of 3, or negative of that is f of 3 minus f of 2, which is the nothing but the integral of 2 to 3 dt, right? So this again is a integration by parts technique. So how do you do that? You multiply 1 comma dt. So this is a trick, very general and very well known trick in our in mathematics and in calculus, that you multiply 1 with it. Why? Because integral of 1 is equal to x, and the derivative of log x is 1 by x. So you will be in turn ending up removing terms. So how you will do that? So you see 1 into x, so you will integrate 1, so you get x or t log t minus integral of t into 1 over t dt, or t log t minus 1. So now if you put the limits 2 to 3, you get 3 log 3 minus 3 minus 2 log 2 minus, or rather plus 2. So because this minus this, right, by fundamental theorem of calculus, f of 3 minus f of 2. So you get as a log of 27 by 4 minus 1. This is your one integral. The second integral is rather simple. You should instantly see it and understand that this is a integration by parts question. Why? Because you see this integral 1 over x square, if you integrate it, you get 1 over x, negative of 1 over x. But in this case, you get a 1 by x. So if when you multiply those two, you will have a polynomial in the denominator. So you will in turn use a directly x to the power n integral rule. So you will integrate this and differentiate this. So this turns out to be, if you integrate this, so integral of 1 over x squared dx is minus 1 by x. So minus 1 by x log x, very good, minus 1 by x is the derivative of this into integral of minus 1 by x dx. So you will end up with having minus 1 by x log x, and this integral is plus x to the power of minus 2 dx, which is equal to minus 1 by x log x minus 1 by x. So you put half and 1. At 1 this goes to 0, so you have only minus 1, and at half you have plus of 2 log 2 plus 2, right? So this is your first integral and this is your second integral. So you add 1 and 2 to get I, which turns out to be minus 1 plus 2 log 2 plus, rather this is minus log 27 by 4 minus 1. So this cancels. So you are left with log of 27 by 4. This is also 4 into 4. This is log 27 by 16. I'll just check this once. So you see this is, if I put half at x, so this is half, right? Not 2. So your if it is half, so this is equal to 1 minus log 2 log 2. Just pardon me for that mistake. This is some simple calculation. We are putting x is equal to minus 2 in this at x is equal to half in this equation and not 2. Anyways, so this was a very nice question where you try to solve by, you solved a definite integral also, and you also did integration by parts. So the next question is using properties of integrals, right? So we'll be using properties of integrals here. Let's see how can you use the properties of integrals to solve this question. So remember in the last class we had done something like this. We had shown f of a plus b minus x integral a to b dx is the integral of f of x. So we had shown geometrically that if one function is like this, a to b, the other function was like this, exactly mirror image at a plus b by 2 between the two functions. So the area remained the same irrespective of which function you integrated. So you see, this is a simple trick that you will be using here. As cosec square x theta, I will be using pi plus 3 plus pi by 6 minus theta into f of 2 sine of 2 pi by 6 plus pi by 3 minus theta, and you have d theta, right? So what is this? This is pi by 2, right? 2 plus 1, 3 by 6, yeah, pi by 2 minus pi by 6 to pi by 3 cosec square pi by 2 minus theta into f of 2 sine of 2 pi by 2 minus theta d theta, right? This is integral of pi by 6 to pi by 3. This becomes sec x, sec theta. Cosec pi by 2 minus theta is sec theta, just like, because it's the inverse of sine, right? Sine pi by 2 minus theta is cos theta, so sec pi by 2 minus theta is cosec is sec theta, and so on. So you have this as f2 sine 2 pi minus theta, 2 pi by 2, so that is sine pi minus theta. So what is sine pi minus theta? So we know if this is theta is less than pi, 0 to pi, so this is your sine pi minus theta, right? So this is your theta. This is same as taking this, right? Because your sine theta, which is perpendicular, which is positive here, by hypotenuse, which is positive here. So both are positive. So this turns out to be sine theta, right? And this is pi by 6 pi by 3 6 square theta f of 2 sine theta. Okay, just 2, pardon me again. So right, if you take 2 theta is between 0 and pi, that's the idea. So what we have over here in this case, it will be pi by 2, and anyways, so this is if you are subtracting pi minus sine pi minus theta is sine theta. So this is equal to I1. So we have shown that I1 is equal to I2. This is a simple trick that we use to compute this definite integral. Okay, so till now what we have done is we have discussed the theory of fundamental theorem of calculus, done problems with respect to Newton-Lebnitz theorem. We have also solved questions related to definite integral, partial fractions. So partial fractions have been solved. We solved partial fractions, we solved integration by parts, and we also solved some definite integrals. The last thing that we'll do today is solving area under the curve. So okay, so let's start doing area under the curve. So what we'll do is, so there are two questions which we'll be doing primarily. So the first question, number 11, is, sorry, so let's copy both these questions and we'll be using them later. So we'll do this too, and then we'll call it a day. See, number 11, you remember, so let's write this equation in terms of y first and then we'll speak. So it's mod y 2 to the power x if I take common, so you get 2 to the power minus 1 is less than equal to 1. So you get is y plus 2 to the power minus 1 is less than equal to 2 to the power minus mod x minus half. Right? So now you remember, this is one equation. We'll look at this in a time from now. So look at this thing now. So what is the first equation or the second curve, this equation? What does it turn out to be? So you see, this is from x is equal to minus half to half, right? This is a wonderful, this is a square which is defined as mod x less than half. So mod x less than half means this equation, right? So sorry for that. So mod x less than half is anything between this, right? Here mod x is less than half. Similarly, anything here is mod y less than half. It's a simple equation. So x less than half is something like this. Remember, x less than half. This is x less than half. So if you do take mod, what we discussed, mod over x, you reflect about the y-axis. Mod over y, you reflect about the x-axis. This is the equation that you get. So now you are told to find the area between this and this. So let us, for this, as the old trick in the first 4 weeks of our session, we have seen take x comma y greater than 0, right? So as x comma y is greater than 0, what we'll do is we'll remove the mod, right, for the time being. 2 to the power minus x minus half. So what x is equal to 0, you see y is less than minus half. 1 minus half is equal to half. Y is less than half. So it's somewhere here. And at x is equal to 1, y is less than equal to 2 to the power minus 1 minus half, which is 0. So at 1, this is half, this is at 1, this will go to 0. And this will be an exponential, right? So 2 to the power, e to the power minus x looks like this. So 2 to the power minus x will also look like this. This is an exponential. 2e is also a real number, 2 to the power 2 point something, 2.73. Whereas 2 is also a real number, so it will look the same. Now, you are, from the old trick, I'm going to take mod on both sides. So once I take a mod on both sides, what will we do? Correct. What we'll do is, we'll be taking the reflection over the x and y axis, because whatever is true for the positive x and positive y is also true for negative x and negative y, because the mod makes all of them symmetric. So now you see, you are told to find the area between them, right? This area, this area, this 4 areas. Now if you, this needs no rocket science to understand that your A1, this area is same as this area and this area, right? So your required area is 4 times A1. So what, just need to find A1. What is A1? A1 we have discussed. So if a top function is f1 and f2, to find the area between these two, we had shown that it's f1 minus f2 dx, right? Because it's the area under the curve and x-axis. So we will, what we are essentially doing, we are subtracting the area of f1 from the area of f2. If we subtract area of f2 from area of f1, you will be left with this area, right? So that's what we'll essentially do. So the first, this top function is half, right? This is y is equal to half, and this function is y is equal to 2 to the power of minus x minus half, right? So this, your integral becomes half minus 2 to the power minus x minus half. This is your f1, this is greater, f1 greater than f2 dx from x is equal to 0 to half. At half, you see they cut, right? At half you want this to be solved. At x is equal to half, you want it to stop. That's solving the integral. So half of half becomes 1. So it's 1 minus 2 to the power minus x dx, 0 to half. So the first integral is very easy to calculate. 1 dx is half only, because integral of dx is from 0 to half is half. and minus of 2 to the power minus x dx, 0 to half. So how do I do this? So we all know the integral of e to the power x dx is equal to e to the power x. What are the minus here? Because you have a minus. Anyways, so you can, what we do is, how do you relate e and any a? So we are trying to find out integral of a to the power x dx is equal to question mark. So how do you do that? So we can do something like derivatives, right? The integral we have seen is a reverse of the derivatives, right? So we'll do is something like this. So we know a to the power x is if it is y. So take log on both sides. You have x log a is equal to log y, or 1 by y dy dx is equal to log a, right? Or dy dx is equal to y log a, or a to the power x log a. Now you see, do you agree that integral of this dx will be your y? If you agree, then you must agree integral of a to the power x log a if I remove dx is equal to, which is y, this is a to the power x by log a, right? Because log a is a constant. Let's see. So this term, this integral becomes 2 to the power minus x dx will become minus of 2 to the power minus x, because we are taking d of minus x in this case, right? 0 to half, and we put a minus on the outside for that, by log 2, right? I hope you understand. From 0 to half, or you can dissolve the sign and invert the limits. So you have 1 minus 2 to the power minus half, or square root of 2, 1 by square root of 2 by 1 by log 2, right? This is your second integral. So what does your total integral look like? The total integral is something like this. So it's first part is half. So area is, so did we find, we found this integral, right? So this is, there's a minus in between. What integral have we found out? We have found the integral of 2 to the power minus x dx, right? 2 to the power minus x dx can be written as minus of, yeah, we have found the integral of this, and we have a minus in between, so it is minus I1. This is minus I, this is I1, right? So it is half minus I1, or half minus 1 by log 2, 1 minus 1 by square root of 2. This is A1. What is area? It will be 4 times 1 by 2, 1 by log 2, 1 minus 1 by root 2. That is the question for us that we are solving. 2 minus 4 by log 2, 1 minus root 2. That I think will solve this question. So it's a very interesting question where we saw that we applied the things that we had used in the first 4 sessions or first 4 tutorials of this lecture series, and we have also used area and also some concepts of integration and fundamental theorem of calculus. So what we have used primarily the way to plot graphs and find area using integration. The last question, number 12, is this. So how does it says that what values of m, x into y is equal to x into 1 minus x and y is equal to mx make up area of 9 by 2. So see, so you will make an area of 9 by 2 in this way. So you see you have a root at 0. This has a root at 0 comma 1, right? So this is something like this, and this is x minus x square, which is a negative. So it's a inverted parabola, right? So it looks something like this. Sorry. So see, at x is equal to 0, what is the tangent of this curve? So I'm writing this for a reason. Dy dx is equal to 1 minus 2x. At x is equal to 0, this is 1, right? So you see y is equal to x, so if m is equal to 1, area is equal to 0 because it's a tangent. Agreed? So but for that we have two cases. Y is less than 1, something like this, where you have this is m is less than 1 if y is equal to mx, right? And you have another case. Let's draw that with a red, something like this, right? This is y is or m is greater than 1, right? If m is greater than 1, you will be forming area below the curve, which will look something like this. So this is your area, right? This is m less than 1, and this is m less than 1, this is m greater than 1, right? So this is the geometric thing that you needed to understand to get this idea. So anything above this line will cut this parabola below, cut parabola below x-axis, and this will or rather for x less than 0 and cut for x greater than 0, where m is greater than or less than 1. So let's solve this question. So the first area, again, let's solve what points does this curve cut this equation. So x into x minus 1 is equal to mx, x is equal to 0 is a solution, and 1 minus x is equal to m. So case 1 we are solving m less than 1. So we have x is equal to 1 minus m. So this point is 1 minus m, right? And this point is also 1 minus m, but m is greater than 1 here. So you're having a negative value, x1, x0. So you see the first integral, which curve is above? This is above. We are still using the derivatives, that lower m means the curve will be this line will be below the curve. So what will be the area? The above curve is x into x1 minus x, the below curve is mx, and area between 0 and 1 minus m dx, and this will be 9 by 2. This solves the question first part. So then let's integrate. So you have x squared by 2 minus x cubed by 3 minus mx squared by 2, 0 to 1 minus m is equal to 9 by 2. A bit of simplification, 1 minus m squared by 2 minus 1 minus m cubed by 2 by 3 minus mx squared by 2. So if this 2 you take common, you get 1 minus m cubed by 2 and 1 minus m cubed by 3 is equal to 9 by 2. So if you take the LCM, you get 6, 1 minus m cubed by 6. So 3 or 1 minus m is equal to 3, or because if you multiply this, you will get 27 here. So cube root of 27 is 3. M is equal to minus 2. So we are seeing that your for this, our assumption that m was positive is wrong. Our m will be something like this. So this is what your m equal to minus 2. So x0 is equal to 1 plus 2 is equal to 3. So this is your area that you are searching for, right? This is your first area, and the second area similarly, case 2, m greater than 1 is this area, right? So in this case we can clearly see this curve is below. So integral of mx 1 minus m greater than 1 to 0 dx is less than 0, right? This is a negative area, is your area of this area, right? A1 minus of 1 minus m to 0 1 minus xx dx is the A2, or area under this curve, A2, and this is your A1. So we are taking a negative here in this case because it is below the x-axis, so all the areas are negative. So in this case, what we will be having, which curve is below? This is the curve that is below. So we have mx minus x into 1 minus x dx from 1 minus m to 0, and this area will be negative. This is a negative area, and that is equal to 9 by 2. So this turns out to be, let's integrate, m square by 2 minus x square by 2 plus x cube by 3, right? 0 to 1 minus m is equal to minus 9 by 2, or you can put 9 by 2 and you can cut this and put directly 1 minus m here, or you can swap, you can dissolve the negative sign and change the limits. So what you have is m into 1 minus m square by 2 minus 1 minus m squared by 2 minus, so m minus 1 cube by 3, right? So this is minus. I put a minus sign on the outside just to account for this is m minus 1. If you write plus, it is 1 minus m. This is, if you take the common, so you will have m minus 1 into 1 minus m squared, so it's always positive, so m minus 1 is equivalent to 1 minus m squared minus m minus 1 cube by 3 is equal to 9 by 2. So you get m minus 1 cube by 6 is equal to 9 by 2. Again you have m minus 1 is equal to 3, m is equal to 4. So m is equal to 4 would be a solution. So x is equal to 1 minus m, this is minus 3. So minus 3 and 3 you are going to integrated. So with this we have solved all the 12 questions. So if you are in case wondering why there are no people in this session, so the first half an hour of the session was recorded in the class, and due to some technical glitch the recording had stopped, the streaming had stopped. So this is a re-recording from question number from the integration by parts question onwards. So till today I'm going to give a summary. We have for the case of integrations, we have completed the fundamental theorem of calculus, the Riemann integrals, saw how the area of the integral is equal to area under a curve is equal to the integral, and integral is the inverse of the derivatives. We have solved Newton-Lebnitz, special case of fundamental theorem of calculus. We have done integration by parts, solved definite integrals, and also solved partial fractions for our case. We have also extensively looked into area under the curve and limit of a sum. For the next week, what we discussed in the classes, we'll be discussing volumes. We'll have we'll go a notch higher, discussing line integrals, surface integrals, and volumes under rotation, or in cases where area is a single variable function. So with that, we'll end our session for today, and hope to see you next week with volumes calculation in one variable calculus, single variable calculus, and we'll also go to line integrals and surface integrals. That's the plan for the remaining 2 sessions. We're almost at the end of the series of tutorials. I hope you are liking it, and thank you.